Hello everyone, I'm Adam Chu. Today I'd like to talk to you about NVIDIA's CPO development. GTC 2026 has just concluded, and some interesting news has emerged. First, we are seeing headlines mentioning copper stays, fiber waits. This has led to a dip in optical communication stocks because the anticipated surge in fiber optic usage might be delayed. The reports suggest that AI chip signals will continue to rely on copper cabling rather than fully transitioning to optical fiber, causing a weakening in the U.S. optical communication sector. The next-generation Feynman processor and the highly integrated Kyber high-density rack architecture are expected to utilize both copper cabling and co-packaged optics CPO simultaneously. This is the first major piece of news. Moving to the second news item. Regarding the scale-up switch portion of the rack, NVIDIA showcased its new Kyber rack. This system is specifically designed for the Rubin Ultra architecture, expected to be introduced in 2027. It will support a high-density platform featuring 576 NVIDIA Rubin Ultra chips. Now, let's look at the diagram on the right, which is a schematic from Jensen Huang. This shows the backplane, specifically the PCB backplane. The Kyber rack utilizes a vertical insertion design for its computing blades, allowing for direct interconnection. Actually, there were already signs of this at GTC 2025 last year. On the left is the standard rack used by the Vera Rubin series. Traditional designs use individual trays, computing trays, and the switches are connected via fiber optics from top to bottom. In these traditional racks, the connection distance is typically between 0.5 to 1 meter, with a lane speed of 200 gigaplex. At those distances, using copper cables would result in significant signal loss. However, with Rubin Ultra, NVIDIA changed the rack architecture from a horizontal layout to a vertical one. By using a PCB midplane, the computing components connect directly to the scale-up switch rack. Because of this direct plug design, the connection distance is drastically reduced, estimated to be less than 10 centimeters. Since the distance is so short, there is no need for optical fiber. The signal loss and conductor loss are limited enough that copper remains a viable and effective solution for scale-up. The diagram below shows TSMC's silicon photonics roadmap, which we can analyze in tandem. TSMC's chiplet documents from 2021 already outlined several applications for silicon photonics. First, it is used in data center scale-out switches. These hit the market late last year, and a newer version will be used for the Vera Rubin series this year. Second is the backplane, the switch. But as mentioned, because the rack has been changed to the vertical Kyber design, the connection distance has been greatly reduced. Therefore, I predict that for the 2028 Feynman processor, we still won't see optical interconnects here. They will likely continue using copper with the vertical Kyber rack. However, the third application, chip-to-chip, is where things change. To my knowledge, when connecting GPUs with CPUs and CX network chips, NVIDIA uses NVLink. For the next generation NVLink 7, speeds are expected to exceed 448 gigabits. At these speeds, traditional PCB copper traces simply won't work, so they will transition to optical electrical OE conversion, likely within the interposer. Finally, we have intra-chip OEIO. This will likely involve 3D stacking. Essentially, the OE components will be vertically stacked onto the GPU die using technologies like TSMC's SoIC, System on Integrated Chips. The advantage of 3D stacking is that the hybrid bonding pitch is extremely small, allowing for very high interconnect density and, consequently, massive bandwidth. I estimate that by 2030, once TSMC's current research enters mass production, we will see 3D stacked OE to maximize transmission bandwidth. These are my personal theories and analysis. If you enjoyed this content, please subscribe, and I'll see you next time.